So let us start the color complex concept, means the concept that will decide or explain why the coordination complex are generally colored. But before starting this topic, let's remember the one of the compound given in the class 10th level, that was I think a blue vitriol I think and green vitriol, called copper sulfate and ferrous sulfate. I think you remember it. The copper sulfate in the condition of anhydrous is a colorless white crystals, white powder called amorphous particles. The same time, the same chapter, you notice that when the copper sulfate pentahydrate written, it is written like a blue color. You should learn why the copper sulfate in anhydrous condition is a colorless or white solid, amorphous solid, but the same copper sulfate in the water look like a blue. Students, the answer behind this is the coordinate complex formation of the copper plus 2 ion with the water molecules. Means when the copper sulfate anhydrous powder is dissolved in the water, it actually form a complex formation with the water molecule, and due to which there is some possibility of the color. The same time, in the class 11th, when we will reach in the class 11, the periodic table chapter reveals about the most of the d block ions, the metal ions, are colored because of some unpaired electron presence there. It's mean the color, the concept of color formation is somewhat depends upon the unpaired electron with the ion, or you can say that unpaired electron present in their complex formation or in their compound formation. Many of the colored compounds around us is actually based on the same concept. This topic can be explained on the basis of crystal field theory, and that's why the same topic is given here. So we can actually give an idea about why there is a color formation in the complexes, different complexes. In fact, that in NCERT, the many of the examples are illustrated. We will take some example from the NCERT also. But before that, let's discuss some basic concept here. Actually, from the crystal field theory, it was confirmed that the d orbital is split into the two different parts. The one part is called lower energy orbitals. The other part called higher energy orbitals. It is very clear, on passing the light, or when the light beam of light passing through the any substance or complex, the color only can be visible or color only can be seen when colored wavelength are reaching to our eyes. Because the detection of color is only depends upon the some kind of pigments and cells present in our eyes. And that's why we are the most complex animals on the planet that can be recognize the color, the different colors in the nature. This is not only depends upon the light formation or the wavelength of light. This is actually the mutually depend upon the pigments and the different cells present in our eyes called rods and cones. These are some kind of cells, the sensitive cells that will decide the color formation in the different complexes or the different substances. So let's leave the biology part. Let's just take the chemistry part and physics part. That is, whenever the blue color wavelength comes near to our eyes, the substance look like a blue. Whenever the substance look like a purple, it means a wavelength that reaching to our eyes must be having some composite wavelength that mix together to form a purple. The red color substance must be known as, because the red color wavelength reaching to our eyes. It's all about which type of wavelength reaching in our eyes that will decide the color formation in the given substances. By the way, okay? Let's discuss why only red color, not blue. Means if the any substance look like red, why only red, not blue or any other color? It depends upon now which wavelength of the radiation can be absorbed by the complex and what complementary wavelength can be emitted by the substance. Means the compound and substance will decide the nature of wavelength emitted from there, and all about it will depend upon the electronic transformation, electronic excitations, the presence of electrons in the unpaired and paired manner, the presence of ligand that will actually decide the difference of this energy gap, and of course the metal nature or the cation nature that will decide the electron present in which type of orbitals. These all factors together will decide the wavelength emitted from the substance at any instant. It's me. This gap of the T2G and EG set for the octahedral complexes, you can see that here the three orbitals, suppose there is one electron are present, one electron is present and some light is passing through the complex formation, compound formation, light H nu. This electron may excite to the some upper energy level. This is called the energy absorbed by the complex formation, complex or compound. But this is not the reason of the color. The reason of the color is when this electron again come back to the lower state, which wavelength can be emitted by the complex or the electron during the returning from the excited state to the lower state. The color of the complex depends upon the emitted light, not the absorbed light. But the nature of the emitted light depend upon the nature of the absorbed light. According to the different theories, it was confirmed that the color of the substance actually is a complementary connection which type of wavelength can be absorbed by any complex. This also depends upon the energy gap. If there is a large energy gap, there must be requirement of high frequency of the radiation, means a low wavelength radiation. Students, it is very clear. If the strong ligand is there, as the started lecture I explained there, if there is a strong ligand, because of the presence of a strong ligand, there will be high energy gap between the upper orbitals and lower orbital that require a much high frequency of the radiation for the excitation of this electron from ground level to the excited level. It's all about the lower wavelength radiation required for this excitement if the energy gap is high, simply in one sentence. The same time, then returning this electron from higher excited level to ground level, the complementary wavelength will emit that will decide the color. And for that, I will take an example from the NCERT book, and that is given there. You can see from the table 9.3 from NCERT, here many of the compound given, and you can see the complementary color emitted by the complex. For example, the one complex is there, the cobalt, chloride and ammonia complex having the color absorbed is yellow, but the complementary color emitted and the complex look like a violet. The same time, many of the other examples also given there, and you can see the some wavelength also given there, some wavelength. The table number 9.3, you should go through that, which type of complementary color can be emitted because of the different color absorbed. No need to learn all these, because during the question they actually given the complementary color, or they actually given the absorbed color. Any one of them they have to be given the question, then we'll ask about the color of the complex formation. Students, the concept behind this is about the transition of unpaired electron from lower level to the higher level, and even both set of orbitals called d orbital set. So this is simply called dd transition. This is called a DD transition. Means electron transit from the lower d orbital to the higher d orbitals only. You should also learn that all these orbitals are actually belonging to the same subcell, so there is not a large energy gap. If there is actually a much large energy gap between the different cells, suppose cells orbitals of S subcell and orbitals of P subcell, the electron must be absorbed energy from the ultraviolet region, and there will be no any color visible for the complex formation. If complex formation or any compound look like a white or colorless, it's mean there is actually excitation of electron having a range of wavelength from the ultraviolet region. For example of the zinc complex, Zn plus 2 complexes, scandium plus 3 complexes, Mn plus 2 complexes, they are actually colorless. As you have seen during the titration also, the potassium permanganate, the purple color, the pink color actually potassium permanganate become colorless because of the Mn plus 2 formation. From Mn plus 7 to Mn plus 2 formation. This transition actually decided by the number of unpaired electron, the energy gap between these two set, and wavelength of the radiation absorbed and complementary wavelength of the radiation emitted by the complex. You can detail on the basis of some more example that is given from the NCERT. I will take one more example to explain this, and the example is nickel. The one of the complex given in the NCERT, that is nickel, the hexa aqua nickel second ion. And let's see what should be the what will be the illustration of the color changing and depending upon the ligand formation. Then we'll explain some more things about this topic. The complex is, look at the complex. This is called ethane 1,2-diamine. It is a didentate ligand when hexa aqua nickel second ion is mixed with ethane 1,2-diamine. The one ligand of this didentate can replace a two water ligand which is a monodentate. So now we have a complex of mixing of ethane 1,2-diamine and 4 water molecules together. You can see the change of color. Here all ligands are water, and now we have one ligand from the ethane 1,2-diamine and the 4 are the monodentate. In the last study lecture, I also explained about the strong field ligand and weak field ligand. Here you should mention these all 6 ligands are weak ligand, and because of weak field ligand there will be a low energy gap between T2Z and EZ set, but introducing a strong ligand that will just increase the energy gap. Because of that, during excitation of electron from lower to the higher energy level, the wavelength of radiation will be changed, and when absorbed wavelength will change, the complementary emitted wavelength also will be changed. That will change the color. That will just change the color. And this is the reason this molecule is green in color and this molecule is a pale blue color. It's mean the color of the complex now depends upon the nature of ligand, because the splitting energy depend upon the ligand nature, the strong field ligand or weak field ligand. The same thing can be also seen by the some more ethane 1,2-diamine when introduced. For the next step, the successive step. See, If in the complex, we are again added one more molecule of the ethane 1,2-diamine, that will just replace the two more water from the complex, and now the complex having two water molecule and two didentate ethane 1,2-diamine. Now the complex known as two water molecule. If you can be write the name of the IUPAC name, there will be the IUPAC name will be diaqua base ethane 1,2-diamine nickel second ion. This is the name of the complex here. That will again change the color, because in the first complex there is only one ethane diamine ligand and four molecule of water. Now there is two molecule of ethane 1,2-diamine and two molecule of water. That will just change the splitting energy again, and that will change the nature of wavelength of the absorbed light and emitted light. And that is the reason why the first complex was pale blue. Now the complex is a blue purple. The complex become blue purple. And if all six water molecules are replaced by the three ethane 1,2-diamine molecule, and now in the last we'll get this molecule. This molecule, on replacing all six molecules, this will be changed the color in the violet. So you can see the color of the complex become from green to blue and from blue to violet. We have three different colors: green, blue, and in the last violet color. Why these colors are there? Because of different wavelength of light absorbed, because of different wavelength of light emitted, because of different splitting energy, because of different ligand, because of different nature of ligand. So all these complex formation and the color concept can be explained on the basis of this crystal field theory. The same time, many other some other examples are given here, like color of some gemstones are because of the some colored D block ions are absorbed by the stones, that will decide the color formation. You are also knowing the color of our blood is because of the complex of the iron Fe plus 3 with some protein molecules, that is called hemoglobin. So many of the colored formation and color of the complex around us is because of the many of the ions of D block and sometimes ions of the F block presence there. This is all about the color of the complex. Students, we can discuss about the limitations also in the same topic. Limitations of the crystal field theory. The limitations is, you should learn first thing. The ligand are believed as a point charge and metal cation. Okay, so the interaction between the point charge and metal cations should be on the basis of the theory based on electrostatic interaction of the point charge and the metal cation. If all these interaction based on electrostatic theory, the electrostatic interaction, how can we explain the coordination bond or covalent nature of the bond formation? Because the theory based on electrostatic repulsion, electrostatic interaction, that is the major limitation of this theory. This theory cannot explain the covalent bond formation nature or covalent nature of the coordinate bond, because electrostatic repulsion or interaction cannot explain about the covalent bond formation and coordinate bond formation. The second thing is about, that is very interesting one. If ligand believed as a point charge, then anions must having a more repulsion comparatively a neutral molecules. As you can see that the carbon monoxide is the most strong field ligand. In spectrochemical series, that is the first ligand which is the most powerful, most strong, that is carbon monoxide. All halides are in the end, that in end of the series. So if this theory based on electrostatic repulsion, then halide must be come forward and must be known as a strong field ligand. But it is seen practically that the anions of the halogens are actually weak field ligand, and because of them there is a weak or low splitting energy created. These are some major limitations are actually seen in this theory. The same thing given in the book also. You can go through that. You can go through that and you can just write the two limitations given in the book at least. Then we can discuss about some questions given here. In-text question. Some in-text question. So this in-text question I will discuss later. We can discuss here also. We have a time now. We have enough time I think. So we can discuss here. I just giving you hint. You can go through the questions. X in-text question number 9.5. Explain on the basis of valency bond theory that nickel tetracyanonickelate second ion with square planar structure is diamagnetic and the Ni tetrachloridonickelate ion with the tetrahedral geometry is paramagnetic. I have already explained about the sum of the complex of nickel. Why there is a paramagnetic nature? Why there is diamagnetic nature? It always depends upon the inner outer complex formation, pairing and unpairing of electron in the d orbitals. So you can go through the valency bond theory explained in the previous lectures, and on the basis of that you can explain why there is paramagnetic and diamagnetic nature of the complex formation in the given question. The next 9.6 question number. The tetrachloridonickelate second is paramagnetic while nickel. The same example I have chosen now. The tetracarbonyl nickel and tetrachloridonickelate ion. Both are actually sp3, but the last one is the tetracarbonyl nickel ion. Sorry, nickel is a paramagnetic, diamagnetic. Is a diamagnetic. Because in the case of nickel having a zero oxidation number, and because of zero oxidation number, the two electrons from the 4s will be going the 3d and all 3 d orbital will be filled. That is the why the 4 orbital from 1s and 3p will participate in the hybridization formation, and that is called sp3 condition. In the case of 9.7, strongly paramagnetic and weakly paramagnetic can be explained on the basis of if the one unpaired electron will be present, that will be a weak paramagnetic. If the 3 or 4 unpaired electron will be present, that is called strong paramagnetic. So in the case of hexaquaferric ion, this is a strongly paramagnetic because weak field ligand. Because of weak field ligand, there will be outer complex formation, and because of that, there will be many other electron will be unpaired. But in the case of hexacyanoferrite ion, this is a weakly paramagnetic because there will be a pairing of electron in the d orbital, but the one electron will remain unpaired because the configuration is d5. When you solve this question, there will be a d5 configuration will come, d5 configuration, and so on pairing of electron, the one electron will remain unpaired. That is called weakly paramagnetic inner complex formation. The same other questions can be explained on the basis of the previous lectures of the crystal field theory and valency band theory. So you can go through the different lectures, the previous lecture to explain all these questions. The next topic, the next lecture will be depending upon the bonding in metal carbonyls. The one of the important topic is there also, bonding in metal carbonyls, and here the one important bond is there given, that is a synergic bond formation. So we will discuss about the bonding in metal carbonyls in the next lecture, and we'll discuss about the formation of synergic bond formation in the carbonyl compounds. So go through the full lecture to discuss the color formation, and if there is any doubt you can ask your doubts right now. I am ending my lecture here only. You can go through the doubts, and if there is any doubts you can ask me.